Comets from humble origins and eyes on ISON. So we're going to talk about comets because there is, of course, Comet ISON coming through past the sun at the end of this month. And there is the great question, is it going to be the comet of the century? And the first question you have to ask about that is, well, what does comet of the century mean? There is actually no scientific definition for a comet of the century, so let me take you through back through the centuries to give you some idea of what the great comets are. First stop is about 1,000 years ago in 1066. Now, what happened in 1066? Thank you, Battle of Hastings, okay? Everybody goes, oh, I remember that. I had to memorize that for my high school history test, right? In the Battle of Hastings in 1066. Also, in 1066 was an appearance of a comet. And this is recorded on the Bayeux Tapestry, which is this 270-foot long embroidered cloth giving the entire history of the Norman invasion of England in 1066. And of course, since the victors get to write the history books, the passage of the comet in April and May of that year was deemed a bad omen for Harold of England because he lost the battle and actually died in the Battle of Hastings in October of that year. The cool thing about this is actually a passage of Comet Halley, although it wasn't actually called Comet Halley until about 700 years later. Fast forward 500 years, and we do the Great Comet of 1577. And here you can see it has this great big long tail stretching here. It's depicted in this woodcut stretching across the city of Prague. We also get these giant tails, the Great Comet of 1680. All right, notice the phrasing, Great Comet of by a year that's 100 years later. And this is, you can see its amazing tail over the city of Rotterdam in the Netherlands. Next up, we have the Great Comet of 1843. Again, this is a woodcut depicted as it is over the Kent in England. Now, in the late 1800s, we didn't have to do woodcuts and paintings. We actually got photography. So the earliest photograph I could find was of the Great Comet of 1882 from the South African Astronomical Observatory. And of course, as an early photograph, you don't get much detail in it, but it's cool that we now can really see what they look like rather than just relying on artists' impressions. We also have that for 1910, Comet Halley. Again, relatively early photograph, so you're seeing not the great sweep of it, but you're seeing all sorts of cool detail from a Harvard plate that was taken in, this was taken in Peru. Well, there are some, of course, recent ones that show these great big tails. Here's one from 1976, Comet West, and you can see that those woodcuts really weren't faking it. The comet tails really can stretch across 10s and 20s and 30 degrees of the sky. We had some really great comets in the 1990s. The one with the longest tail, I was told, is 1996 in Comet Hyakutake. And the ion tail on this was measured to be about 550 million kilometers long. Longest tail. That's several astronomical units. Now, of course, this picture doesn't, of course, encapsulate the whole tail, but that's what they tell me, that it set the record for the longest tail. Finally, we have some in relatively recent years. 2011, this is Comet Lovejoy, and again, you can see this amazing tail stretching across the sky. Anybody see Comet Lovejoy? 1, 2, fantastic. You must have gone down to the southern hemisphere because it was a southern hemisphere comet. All right, we didn't get any. We've had 2 great comets in this century. Both of them have been visible only from the southern hemisphere, have not been able to see from the northern hemisphere. This, by the way, is the lights of Santiago in Chile underneath Comet Lovejoy. So if you go to Wikipedia, there's a list of great comets, and it gives you sort of a feeling of the various comets over the centuries and some of their names. But of course, it's not that terribly scientific. It's Wikipedia. That's what do you expect? Slightly more scientifically, or much more scientifically, is a list compiled by Don Yeomans called Great Comets in History, in which he finds 71 comets over the last 2,400 years. I actually updated that to be 72 with Comet Lovejoy in 2011 because he did his work in April 2007. In this list, there are 22 appearances of Comet Halley, while no other comet appears more than once. So that gives you an idea of just how important Comet Halley has been in our understanding and development of comets. Well, the characteristics gleaned from his notes are that their tails can be up to 100 degrees long, that some are so bright that they become visible during daylight while the sun is still up. And many of them appear to be sun grazers. And sun grazers mean that they come very, very close to the sun. Their orbits bring them real close to the sun. I'll show you a couple of those in a few minutes. Because they pass close to the sun, the stability of the comets are in question, and several of these comets have actually broken into pieces. They were observed that after they passed by the sun, they broke into 2, 3, or 4 pieces. And in particular, there is a particular family of comets that appears to be a source of several great comets. It's called the Comets family. And it's a family of sun grazers that was noticed by astronomers that several of the comets, there are now 9 comets that have the similar orbits. All right, if you trace back their orbits, all 9 of these comets have similar orbits. And so the postulation is that there was a much larger comet that broke into a lot of smaller comets hundreds of years ago. And these comets here in the Comets family are all the pieces of that much larger comet. And of the Comets family, the 5 here that I've got bold in yellow, 1843, 1882, 65, that's Ikeya Seki, 1970, and 2011, which is Lovejoy, have all been great comets. So the Comets family has a bunch of cometary royalty in it, in the Comets family of comets. Now, what's also interesting is the statistics, and it goes sort of the way you might think. You know, up until the Renaissance, there's only 1 or 3 each century, you know, relatively incomplete. But you start getting more as we start paying more attention, although the 1700s, there are still only 2. But in the 1800s and the 1900s, you get 8 and 9. And as I said, we've already had 2 in the 2000s. So the phrase comet of the century doesn't really apply because on average, we sort of get one once every decade. Of course, in the media, calling it Comet of the Decade doesn't sound so amazing, so Comet of the Century is probably going to stay in our modern media. Now, which one of these was the greatest comet? I can tell you without hesitation, the greatest comet is the one you see yourself. All right? Because you can see all the pictures that you want, but the one that you see with your own eyes is really the greatest comet. It's such a wonderful experience. And for me, that was Comet Hale-Bopp in 1997. All right? I was at the Columbia University at that time. I was living in Columbia University housing at 113th Street in Manhattan. And I come out of the apartment building, and I look down the street. Now, I'm 7 blocks from the Hudson River. Okay, I'm far away from the Hudson River, and there's all these city lights. And what do I see hanging there between the buildings over the Hudson? I saw Comet Hale-Bopp. And that was a really powerful experience to me. Now, of course, being a geek, I immediately just walked straight down to the river and saw, you know, over the lights of New Jersey. But being able to see Comet Hale-Bopp with the lights of the city was a very powerful experience to me, and it was certainly my favorite, the brightest and most impression I've had of a comet in my lifetime. Hopefully, Comet ISON will surpass it, or some other comet, because I'd hate it if you know, the best comet I ever saw is already in my past. So let's get to these comets and talk about what they're really made of, okay? Because we're not really seeing the comet itself when we see these bright comets. The heart of a comet, instead of looking like this big streak across the sky, really looks more like this. This is the nucleus of Comet Wild 2. And in order to see it, you can't see it with just up in the sky. You actually have to go there. All right? This is the only times we've been able to see the nucleuses of comet is when we have a space mission that travels to them. Here's another one. This is Comet Hartley 2, the nucleus of Comet Hartley 2. It looks a bit like a bowling pin. And then we've also got another bowling pin, Comet Borrelly. I actually can call, these are actually very well known simply because there are only 5 comet nuclei that we've seen up close. That's it. 5 of them, and they're all here to scale. We've got Borley, Wild 2, and Hartley 2. We've also got Halley and Temple 1, which I will talk about both in just a few minutes. The point of this slide here is, however, to give you a scale of these objects. They are only a few miles across. The largest of comet nuclei are probably tens of miles across, not very large. So a comet in itself is really a relatively small object. And when you look at the shapes of these, well, they look rather similar to another class of objects. On the left is Comet Borley, and on the right is Gaspra, an asteroid. So in shape, at least, comets look a lot like asteroids, which of course begs the question, well, what's the difference between a comet nucleus and an asteroid? Well, the simple thing is that the comet nuclei formed in the outer solar system, so they're mostly ices with a little bit of rock and dust mixed in, actually a lot of dust probably, whereas the asteroids formed in the inner solar system, and they're much more rock, and they may have a little bit of ice. So for elementary school kids, we simply say, okay, comets are ice with some rock, asteroids are rock with some ice. But they are both the flotsam and jetsam, the things left over from the formation of the solar system. So you can see that comets look a lot like asteroids, but did you know that asteroids can also look a lot like comets? Here's a picture of an object called P2010A2. And this type of name is what we give to a comet, something that has a tail. And you can see a wonderful tail along here. But if we zoom into this region, we can see that it doesn't look like a comet, because a comet is supposed to have a coma that gets smoothly swept back into a tail. Instead, you've got this sort of X-shaped pattern. What's going on here? This is not a comet. What we believe happened here is the collision of two asteroids. Asteroids collided, and the dust kicked off in that collision, then gets swept back and forms this complex pattern here that then gets swept back into this tail. And you think, oh, well, that's just a special exception. No, actually there are more, and last Thursday, Hubble released these two amazing images of an asteroid called P2013 P5, all right, where it's got not 1, 2, 3, 4, and 5, they tell me 6 tails. I can't quite see them all here in these images. It's got 6 tails going off around it, and we have never seen anything like it. We truly don't actually understand exactly what's going on here. I'm going to have to say, if you want more information, go to the press release on Hubble site to see more about it. But it underscores the idea that these tails that we always associate with comets, we can also associate them a little bit with asteroids. Okay, now, here is something where we wanted to look inside that comet nucleus. We believe that these comets and the asteroids are leftovers from the formation of the solar system. And it's sort of hoped that if we looked inside them, maybe we could understand what the original solar nebula was made out of. So we had a smash hit, or as I like to call it, washing machine crashes into iceberg at 25,000 miles per hour. This was the Deep Impact mission, and it went to Comet Tempel 1. And basically, as the Deep Impact mission passed by Comet Tempel 1, it released a probe about the size and weight of a washing machine that would smash into Comet Tempel 1. You're looking at the camera on that probe as it approaches, and I've got it marked to 107 here in the upper right-hand corner. And as it gets further, it's going to go into this region, and it's going to go in towards this crater here. Let's go in towards the lip of this crater and get closer and closer and closer until it becomes all blurred out and the probe smashes into the comet. Of course, the Deep Impact mission was passing by, monitored it, of course, and this is before impact. And then you can see the impact, and we've got 16 of these, so I'm going to go through them relatively quickly. And slowly, the impact exposed material that was inside that comet. And stuff blew away. All right, now I'm going to rewind, go back to the beginning, and show you the most important slides. Okay? So here's the impact. Now watch these next 3 slides. Here, here, here. You see that poof of material? That poof of material, that initial poof of material, told us that the probe went really deep inside, that it wasn't very solid on the surface, that it was a very porous undersurface. We know that comets have these relatively crusty surfaces, but we didn't know what was underneath it, and told it that it was very porous underneath, and so we get this initial plume of material, and then the secondary plume of material that spreads out. And so looking at that, we're able to tell that the material underneath the surface had a very fine consistency, and one scientist described it as being about the consistency of talcum powder, which of course meant that it spread out across space. So the Hubble Space Telescope was observing. This is the pre-impact observation, and after impact, it brightened, and then another 10 minutes, the material started to flow away, and further, and by about an hour and a half afterwards, there was this humongous spray of material. So the Deep Impact mission was able to send a probe, smash it into a comet nucleus, and expose some of the material from the inside, shows its consistency, but unfortunately, it also showed that the material was not pristine. Was not the pristine material from the origin of the solar system, was not the composition of the solar nebula. It had actually been processed relatively deep inside the comet, so that promise idea of looking at the material from the original solar nebula was not fulfilled, but at least understanding the structure, the interior structure of a comet was accomplished in Deep Impact. Next up, dust in the solar wind. So that other comet nucleus that we haven't looked at yet is Comet Halley, observed in 1986 by the Giotto mission. And here you can see the nucleus of Halley. It's about 8 miles across. But you also see jets of material. As the comet nucleus passes in close to the sun, generally within the asteroid belt or within the orbit of Mars, it gets warm enough for the ices in the nucleus to sublimate, go directly from ices to gases. And that generally happens by the emission of these jets of gases. And those jets of gases then become this cloud around the comet, which we call the coma. And this is a great picture of Comet Neat, and you can see this beautiful coma, all of these gases surrounding the comet. Now, I told you that the comet nucleus was only a few miles across, maybe 10 miles across. The coma can be 1,000 to 10,000 miles across. Okay, 1,000 to 10,000 times larger than the nucleus. So you know that when you're seeing this, you are not seeing the comet itself. You're just seeing the cloud of gases, ices and dust gases around the comet. You're not seeing the comet itself. Then that cloud then gets swept back into a tail. And to understand how that happens, all right, we got the phone done? Cool, no problem. All right, to understand how it gets swept back into the tail, we got to look at the sun. This is the photosphere of the sun, and it looks relatively quiet, except for it's got a few pimples on it. All right, of course, each of those pimples is the size of our entire planet, which is, you know, the sun has pimples the size of our planet. But it's the visible photosphere looks relatively quiet. Of course, we know the surface of the sun is nowhere near that quiet, and we know because sometimes the moon passes in front of the sun. And when the moon passes totally in front of the sun, during a total eclipse, you're able to see the outer atmosphere of the sun, what we call the solar corona. So during a total solar eclipse, you can see that solar corona, but what I can't show you in an individual image is that solar corona is extremely active. Fortunately, we have satellites up there watching it, and this movie is one of my favorite movies, and it shows you the atmosphere, the activity in the solar corona over the course of 1 month. This is 1 month in the life of the sun, and it's not chosen to be a particularly active month or a particularly dead month. It's just 1 month in the life of the sun. And you can see all of those striations are actually outflows of material going away from the sun. This is the sun's atmosphere expanding into interplanetary space. This is the genesis of the solar wind, the wind that blows out from the sun and across interplanetary space. Well, that solar wind, as it crosses interplanetary space, will then take the cloud of gases around a comet and then sweep them back into these extremely long tails. Matter of fact, it doesn't do just one tail. This is a comet Ikea in 65. This is with one of those Kreutz family comets. But it actually creates two tails, as shown in this picture of Hale-Bopp. The straight and blue tail is the ion tail. As these gases are emitted from the comet, they can be ionized by the ultraviolet radiation of the sun, and then the magnetic field of the solar wind pushes them back quickly and straight, and you get a long, straight ion tail. The stuff that doesn't get ionized, doesn't have an electrical charge, is on the dust tail, and that gets pushed back mainly by radiation pressure from the sun, and that can actually have a curvature to it because it sort of lags. It goes out at a much slower pace, all right, and sort of lags and creates a curvature along its path. Now, since the tails are being pushed by the sun, of course, the tails will always push away from the sun. A good demonstration of that is this movie of Comet Neat, again from Soho, and you can see the tail swinging around as the comet passes the sun. Play it for you again. The tail swings around as the comet passes the sun. The tail does not follow along the orbital path as so many might naturally assume. Cats in this manner are like dogs, that sometimes they chase their tails. Matter of fact, comets, as they exit away from the sun, are always chasing their tails away from the sun. The other cool thing is that as it sweeps past the sun, that dust tail, oh, sorry, here's this, to show you that in a single image. But as they sweep past the sun, you can get some amazing pics, and this is one of the most amazing pics, Comet McNaught in 2007. That's the other great comet of this century. And you can see the dust tail as it swung past through perihelion, creating this big, huge, long arc, again, only observable in the southern hemisphere. Shucks for the rest of us here. But this was an absolutely amazing comet, and this is it out over the Pacific Ocean off the coast of South America. Now, these comets are interplanetary interlopers, all right? And just to give you scale, here is the orbit of Jupiter, Mars, Earth, Venus, and Mercury, okay? Working out to Jupiter. This is the scale. And inside there, in between the orbits of Mars and Jupiter, we have the asteroid belt. Now, of course, I can tell you there's an asteroid belt, but let me show you a plot of all the asteroids in the asteroid belt. This is from the Minor Planet Center at the same scale. And all of these green things here, over 300,000 of them, are the main belt asteroids. All right, now, of course, when they're plotted really, really densely like this, you know, the points are much, much bigger than the objects really are. It looks like there's an amazing morass of them. I have to say always when I present this plot that the average distance between asteroids, because the scale here is about 1 billion miles, the average distances between asteroids is about 1 million miles. Okay, now those of us who grew up on Star Wars, remember The Empire Strikes Back? And the chase through the asteroid belt, and they're swimming in and out of asteroids, and they crash and everything all over the place, right? Again, of course, that's science fiction, not science. Even traveling at 1/10 the speed of light, the time it would take to go from one asteroid to the next asteroid would be about 1 minute. And it really wouldn't make for a good chase scene. Sorry, George Lucas, okay? Scientific truth doesn't support that scene, but hey, it's fantasy. It's meant to be. You'll also notice these blue congregations here. These are called the Trojan asteroids, and they're kept in the Lagrange points of Jupiter. And the Lagrange points are simply just gravitationally stable points between the Sun, Jupiter, and Jupiter's gravity. And it's about 60 degrees behind and 60 degrees in front of Jupiter, and you get a collection of asteroids going there. Then the interesting asteroids to look at are these red ones down in here. And so I'm going to zoom in on those. All right, and again, here where it's Mercury, Venus, Earth, and Mars. And the red ones are the Earth-crossing asteroids. These are potentially hazardous asteroids. But again, space is really, really, really big. So there really isn't much chance of any one of these coming by Earth. I think the next one coming even relatively close is in 2038. I haven't kept up with it because it's not imminent whatsoever. And of course, the orbits of these do change slowly over time. So by the time 2038 comes along, it may not actually be hazardous to us. It's not even hazardous. It's not even coming as close as the moon is. All right, that's the current state of the knowledge. But I use this to sort of show you, all right, these are the Earth-crossing asteroids. Here in the same plot is the Earth-crossing comets. Here are all the comets on the interior of the solar system. And you can see they're much, much far fewer. We're not just plotting the points for the comets, we're actually plotting their entire orbit. But if I back out to the orbit of Neptune and show you the whole solar system, you can see that, like the asteroids, there is a main section of comets in the interior of the solar system. These are your periodic comets. So there is a main belt of comets that is roughly coincident with the main belt of asteroids. So you got a whole bunch of small comets mixed in with the asteroids, not anywhere near as many as we have asteroids. If I flip this diagram on its side so you can see the plane of the solar system, you can see there are a few of these that are out of the plane of the periodic comets, but they're not really part of the main belt. They're actually the anomalies. And just for your edification, Comet Halley is one of those anomalies. It actually is one of these ones over here with the big long orbits stretched down and out. All right? Whereas most of the main belt comets are in the center, nice, relatively flat orbits. So, as we look at Comet Lemon from, I think it was March of this year, I have to ask you, why are there any short period comets? Why are there any short period comets? Think about this. If a comet loses like 1/1,000,000th of its original mass every time it passes by the sun, and it orbits the sun in less than 200 years, then in 200 million years, that comet will be gone. Right? If it's losing material as it passes by the sun, it's going to disappear on a time scale of millions to hundreds of millions of years. So, the solar system is 4.7 billion years old. How can there be any short period comets? They should all be gone. The answer is, of course, that there has to be some resupply. Somebody's got to be restocking the shelves at Amazon.com so we can get new comets, right? Well, where do they come from? They come from a region of the solar system called the Kuiper Belt. Now, this diagram starts with Jupiter, Saturn, Uranus, and Neptune. And all of these red, white, and purple dots out here, every single one of them, except one, has been discovered since 1992. This is the Kuiper Belt in the solar system. And that one exception is this guy right here, which is Pluto. It was discovered in 1930. But all the rest of Pluto's family out here in the Kuiper Belt has been discovered in the last 2 decades. And there are thousands of these objects. They're small, they're icy, they've got elongated orbits, they've got tilted orbits. And sometimes their orbits take them too close to Neptune, and they get they're gravitationally get perturbed inward. And then they may go past other giant planets, especially Jupiter, perturb their orbits, and they slowly migrate inward, such as these orange ones here, which are called centaurs, which we believe are objects in the process of migrating in or migrating out. So these orbits migrate, and they can come in and resupply the short period comets. So the Kuiper Belt is our source of short period comets. Now, if I say the phrase short period comets, there also has to be long period comets. And to get those, we have to go to the ends of the solar system. So, this is a plot of the long period comets, and we'll take a look at the scales down here. Again, this is Jupiter, Saturn, Uranus, and Neptune's orbits. All right, the scale here is 50 astronomical units, where 1 astronomical unit is the distance between Earth and the Sun. Neptune, for scale, is 30 astronomical units. It's roughly a perfect circle, about 30 astronomical units in radius. So, where do these things end? Not a single one of these things ends inside this box. You actually have up to a box out to 10,000 astronomical units to find the orbits of the long period comets. So they've got some really, really, really long orbits. Now, this is just one visual. Let me show you some evidence for for the cloud of comets that we suspect exist. So, here we have the comet number of comets, and up here is their orbital period. And the dividing line is set at 200 years. That's sort of arbitrary. But you'll notice there is a peak of comets down here around 7 years. These are the short period comets. And those are the ones that are in the main belt of comets. But we also have a peak up here, a much, much, much larger peak with the orbital periods stretching towards infinity, which means they're thousands to tens of thousands to hundreds of thousands of years for their orbital period. So most of the comets we have ever seen are long period comets. All right? And the eccentricity, the shape of their orbits, is really, really long. All right? 0 on this plot would be a perfect circle. 1 on this plot would be a straight line. Where do we find most of the orbits? Even amongst the short period comets, most of them are highly elliptical, highly eccentric, really elongated orbits amongst these comets, which you might expect from something that has been tidally perturbed. Gravity has moved their orbits around. If we take the orbital inclination, now this is the tilt of the orbit. So the orbit flat would be 0 in the plane, and then tilted up to 90, and then all the way around to 180. Okay, so we've got the orbital tilt. So we have a peak down here at low inclinations, which is the short period comets that are in that main belt. Then we have a roughly smooth distribution, a flat distribution, so the long period comets are all at relatively even eccentricities, except we have a deficit over here towards all the way flipped over and going backwards in the plane, what we call retrograde. So the short period comets generally have prograde orbits, not so many retrograde orbits. But the long period comets come from every different inclination on the sky. They also come from every direction on the sky. So we got this one orbit, one angle, but we also have this angle, or orbiting around, okay? And that's what we call the longitude of the ascending node, which is a big fancy thing just to say, think of the other angle. All right, and you can see that's relatively flat across the full 360 degrees. So we've got these comets. Most of them have really long periods. They have really stretched out orbits. They come from all inclinations. They come from all angles. What model do you have to get from that data? You get a cloud of comets, and a cloud that extends really, really far out. Now, caution, this diagram has a logarithmic scale, all right? 1, 10, 100, 1,000, 10,000, 100,000, all right? It's a little hard to interpret because the planets are all in here out to 30 AU, but the Oort cloud extends out to 50,000 AU, over 1,000 times farther from the sun than the Kuiper belt. So our short period comets go out to about 50 AU. The long period comets go out to about 50,000 AU. And that's the cloud, the distribution of comets that you get from those series of plots of the data. So, you may have heard about Voyager. Voyager was recently reported to have left the solar system. And if you heard that, they were lying to you. It has not left the solar system, but it has entered interplanetary space. Let me review that. Here, the Voyagers were launched in 1977. They both went past Jupiter and Saturn, and then Voyager 2 went past Uranus and Neptune, and then they kept on going throughout the solar system. And they have continued to fly out of the solar system, and what was announced was actually that Voyager 1 has just passed outside the boundary of the solar wind. So that pressure from the solar wind blowing out across interplanetary space, at some point that pressure from the wind is going to meet the interstellar medium, the material in between the stars, and the pressure is going to equalize. As the pressure goes down from the solar wind and it meets the pressure from the interstellar medium, and at some point you're going to cross a boundary which we call the heliopause, which is the edge of the solar wind, and you'll get into interstellar space. It has been shown definitively that in August 2012, Voyager 1 passed across the heliopause and has now entered interstellar space. But that does not, as much of the media has incorrectly interpreted, mean that it has left the solar system. Because you can see that Voyager 1 is only about 125 astronomical units away from the sun. Whereas the Oort cloud, which is still gravitationally bound to the sun, if you take the gravitational definition of the edge of the solar system, it extends out to 50,000 astronomical units. So Voyager 1 will actually have to travel for another 40,000 years before it leaves the gravitational edge of the solar system, although it has left the pressure edge. The end of is now outside of the solar wind and in interstellar space. And what this diagram, again, it's logarithmic on its axis, shows nicely is that the Oort cloud actually extends about a quarter of the way to the nearest star, Alpha Centauri. It extends almost a light year out into space in the Oort cloud, and the nearest star is about 4.25 light years away. So, these great comets really do have humble origins. You see these fantastic appearances on the sky, but yet they come from the edges, the outskirts, the rural, the nowheresville of the solar system. The short period comets coming from the Kuiper belt out beyond Neptune, and the long period comets coming from the Oort cloud extending well out into interstellar space. Now, let's get to the hot topic of the moment. Comet ISON coming soon to a sky near you. So here is a picture of that comet. And although we call it Comet ISON, it really should be called Comet Nevsky-Novichenok, because Nevsky and Novichenok are the two guys who found it. And this is a picture of them with their 16-inch telescope that they used to discover it. They found it in September of 2012, and it's reported as C2012 S1, in parentheses, ISON. ISON standing for International Scientific Optical Network, which is the group of which these two astronomers were part of. Unfortunately, the media got a hold of it, saw ISON in parentheses, and said, oh, that's its name, it's Comet ISON. And it stuck. And even though it should be called Comet Nevsky-Novichenok, we give up. Okay? It has been so ingrained. Even on Hubble site, you'll find we have an ISON blog. It's not the Nevsky-Novichenok blog. Okay? It's the ISON blog. And sorry, guys, your names don't go down in history like that, unfortunately, because the media finds ISON much easier to use in their stories. But the reason why this comet has caused so much attention is because it's going to pass really close to the sun. All right? This is Comet Neat as it passed close to the sun. You can see how close it got. Comet ISON is going to pass this close. It's going to pass 2.7 solar radii away from the center of the sun. All right, so you can see it's going to pass really close to the sun. It's going to be one of these sun-grazing comets. And actually, we were wondering, is it a Kreutz family comet? Is it like one of these other sun-grazing comets? Well, its orbit is actually very similar to the great comet of 1680. And at one point, there was a hypothesis, maybe it is another comet in that same orbit. Actually, it turns out that the orbits are distinct enough that we don't believe that the two comets are related. But since its orbit is like 1680, and 1680 put on such a great show, well, we're really looking for something cool. So we've been following Comet ISON ever since its discovery. Here are Hubble's two images from the spring, April 10th, 2013, and May 8th of 2013. And Hubble, was able to get reasonable images of it, but of course Hubble can't monitor it. The international group of astronomers, especially amateur astronomers, have been tracking this like crazy, and we have amazing track records of it. So it was discovered here in September of 2012. And over these points over here on the left-hand side were actually pre-discovery observations. They went back in the records and found observations that had it. And you can see it's been greatly tracked throughout this. Now you can see this green line that I've drawn in here. That's the magical 6th magnitude, which is nominally how bright it needs to get for you to see it without a telescope. We call that naked eye brightness, around 6th magnitude. All right. And if we zoom in onto this central region here, you can see what happened. That Comet ISON was brightening according to one curve, and then it failed to follow that curve. And right here, there is a recalibration of the curve, and then it seems to be following this second red curve on up. And I have to say this is a fantastic plot from a gentleman named Seiichi Yoshida, and it's updated as of last Saturday. So this is fresh and current. And as we go into perihelion, which occurs on Thanksgiving of this month, November 28th, you can see that we are getting up to 8th magnitude, very tantalizingly close to that magical 6th magnitude limit. It looks like there will be a period where it will be naked eye bright. And that period appears to be from around, I don't know, the 20th of November on through to about the 20th of December. Okay? Unfortunately, in November, we get the full moon on, I think it's November 15th. November 17th. November 17th is the full moon, and the moon is going to start interfering with ISON observations starting around the 15th. So before ISON becomes naked eye bright in November, we're going to have to deal with the moon. All right, and that may cause problems. Doesn't mean you won't be able to see it, but it just means that the moon will be actually brightening the sky. Fortunately, we get new moon on December 2nd, and so throughout this period, there should be the moon will not be interfering with your observations. So there is a small window of about a month when Comet ISON should be naked eye bright, if it keeps on following this track, which it has followed very nicely for the past month or so. Unfortunately, the caveat to all this is that for comets, breaking up is not hard to do. Comets can go off in a variety of ways. Now, this is a cool thing. This is actually Comet Encke, okay? And I'm going to play this movie and watch it carefully because it's going to lose its tail. There's going to be a coronal mass ejection and a tail disconnection event. And there's the coronal mass ejection, and it just rips off the tail of Comet Encke. Did you see that? I'll play it again. But it's kind of cool to see the comet interacting with the solar wind. Again, here's the comet, there's the big coronal mass, and rips the tail off of Comet Encke as it's passing through. So comets can lose their tails, all right? And I have a tail reconnection event. It can actually happen in even more startling fashion, as happened for this comet, Comet Lovejoy, in 2011. I just threw this image in because it's just so cool to be able to get the telescope and the comet in the same pic. As it passed by the sun, it went really, really close. It went that close, 1.2 solar radii. Comet Lovejoy was not expected to survive its pass by the sun. Of course, we have those satellites to watch it, and this is a fantastic combination of the LASCO C3, the LASCO C2, and the EIT 304 angstrom instruments on SOHO. 3 different instruments on SOHO combined to follow Comet Lovejoy as it passes in and passes even closer. And then it passes right by, this is it as it's near perihelion. Okay, so the comet is not seen, it's near perihelion. Then it appears after perihelion. See that dot right there, just to about the 3 o'clock side of the sun? That's Comet Lovejoy. Here on the left-hand side of the sun is its tail. Its tail got totally ripped off as it did that really close passage by the sun. However, as it got further away, its tail redeveloped. You develop that full dust tail, and by the time it passed out of C3, you can see not only the dust tail, but also the straight ion tail redevelop on Comet Lovejoy. Now that's kind of cool in these 8 pictures that I just showed you, but it's even cooler when I put it in motion in the movie. So here's Lovejoy passing in. It really takes a very quick pass by the sun, comes back out, and redevelops its tail. So comets can actually lose their tails, but even more so than that, comets can totally break apart. This is Comet Schwarzmann-Wachmann 3, a really fun one to say. Never fails to get a little bit of a giggle. Schwarzmann-Wachmann 3. And this is an observation from the ground-based where you can see fragments B, G, and R. Okay? This comet had already broken up, but Hubble was able to examine fragment B and see the extent of the breakup. And so this is Hubble's image of fragment B, and you can see the main comet and all the particles of it. And we got 3 images over the course of several days, seeing all of the small pieces of the comet that are breaking apart and going off of it. And the worry is that Comet ISON is passing so close to the sun, if it is not a compact and well held together nucleus, it could break apart. Of course, it could also suffer a more egregious fate, although we don't expect it for this. There are some comets that disappear entirely. Here is more from SOHO. There are 2 comets down here that pass in and are never seen again. All right, here this is on a loop. They're going to pass in again. And it looks like the sun burps, right? Yum, love them comets, okay? Actually, that's not, the coronal mass ejection is just fortuitous. It is not related to the comets passing into the sun. These are the really close sun grazers that just pass in and we assume are evaporated. They can be very tiny comets. As I was talking to somebody before the lecture, the SOHO satellite has discovered about 2,400 such comets. All right, they have been, by staring at the sun, they're able to see these sun grazers. They've discovered over 2,000 comets, and I'm told that 83% of them are in the Kreutz family of sun grazers. So cool, we got these satellites that does discovering comets, but some comets disappear forever on their passage by the sun. So we've got eyes on ISON. Is it going to hang together? Is it going to break up? There was some paper out over the scientific paper out over the summer saying that Comet ISON was going to break up and then it was going to start dropping down. They used some wonderful data to support it. And what did we find? Well, first, Comet ISON is not going to pass close to Earth. It's not going to get anywhere near Earth. It's not going to even closer to Earth than Venus gets. Venus gets closer than ISON will get. But it did actually pass very close to Mars in October. And we have missions to Mars. Here is one. This is a self-portrait of the rover Curiosity. And you say, well, wait a minute. Curiosity is meant to look at the ground. It's, it's meant to explore. It can't do astronomical observations. Wrong. Curiosity did an amazing astronomical observation. It looked at a solar eclipse from Mars. This is a solar eclipse, the Martian moon Phobos, passing in front of the sun as seen by Curiosity. And I have to give the Curiosity team mega kudos for this, because they are able to position Curiosity in that right spot on the surface of Mars to be able to see Phobos pass across the sun. So Curiosity can do a little bit of astronomical observations, not just look at rocks on the surface of Mars. And so people went crazy thinking, wow, what would it really look like if you were on the surface of Mars and you got the Martian terrain here and you could set ISON up in the sky when it's only 7 million miles away. Or even you could possibly have both Earth and ISON up above the horizon at the same time. Didn't happen, sorry. While Curiosity has the capability to see the sun, which is a really bright object, it did not have the sensitivity to see Comet ISON. And particularly since Comet ISON was nowhere near as bright as people had hoped it might be, even from the 7 million miles away on Mars. However, there was a telescope on Mars capable of it. It is the Mars Reconnaissance Orbiter, which is the largest telescope ever launched into deep space. It's a half-meter telescope. And its job is to survey Mars, look down at it, and really get the high-resolution images of the Mars surface. And so you could imagine taking that telescope and pointing it up at the sky and observing ISON. Now, it's a little bit like taking Landsat and repurposing it to do what Hubble does, but, these guys are smart and they're able to do it. And they're able to get a picture of ISON. Are you ready for it? There it is. Yeah, it's a little underwhelming, but they were actually able to measure, to get a picture of ISON from Mars. Now, they were conservative. They didn't want to overexpose it. They were trying to see if it was large enough to fill a few pixels, and they wanted to actually see just the nucleus. They didn't want to see the coma. This is why this is a relatively faint image. Turns out that the scale of pixel at this distance was about 8 kilometers per pixel. All right, and this image shows that, unfortunately, ISON is smaller than that. The estimate for the size of ISON is about 3 miles across. All right, so we didn't show that, but it also got us a little worried that maybe it's too small, because a larger comet is more likely to survive perihelion passage. All right, so was ISON breaking up? We had this paper out there saying it was going to break up. Fortunately, Hubble came through on October 9th and took this image, and we can definitively say with Hubble's resolution that Comet ISON was not breaking up. Okay, Comet ISON is held together, and you see this beautiful picture. So we've been watching ISON for several months now, and I found this beautiful series of images from this photographer in England named Damien Peach. And so here it is in March of 2013. You can see how faint it is there. And again, in September, it gets a little bit brighter there. And then in September 24th, and then you get October 11th. And it starts looking really cool. So you can see what the amateur astronomers have been doing following it there. The other thing you can see is that it's green. Now, is this a trick of what their photography? No, it actually is green. Lots of comets are green. And the reason is because there is cyanogen and diatomic carbon in the gases coming out from the comet. And when hit with sunlight, they glow a green color. Okay, when you hit them with high energy sunlight, they glow a green color. All right, well, diatomic carbon is just C2, but cyanogen, that's in the cyanide family. Cyanide in the comet. Quick, we better get our comet pills so that we'll be safe. This is not a joke. This is from 1910 when Comet Halley came through, and Earth was going to pass right through the tail of Comet Halley. And there was, of course, there is hydrogen cyanide, there is cyanogen in the tail. And so hucksters went around selling anti-comet pills for only 25 cents each. And 25 cents in 1910 was a serious amount of money. And people, of course, they also sold gas masks and anti-comet umbrellas or anything to save you from these noxious gases. And of course, everybody remembers the millions of people who did not die during the passage of Comet Halley in 1910. The gases in the comet tail are so diffuse they have no impact whatsoever, so you do not need to get your comet pills this year or any other year. I got one more cool pic for you. This is from October 24th. This is Comet ISON, and this is Galaxy Messier 95. Really cool. Another pic from Damien Peach. You can find so many cool ISON images out there. I could give a whole lecture just talking about the cool pics, but there's a lot out there. The internet has made it fantastic for doing research on these comets. One last thing is something that was pointed out this weekend, that Comet ISON right now is not the brightest comet in the sky. There are 4 comets up in the morning, and the brightest one is actually another comet Lovejoy, discovered by the same astronomer Terry Lovejoy, but this is C 2013 R1 Lovejoy, which was only discovered in September, has brightened really quickly, and currently, as of November 7th, it was slightly brighter than ISON, although we expect and hope that ISON, since it's a sun grazer, will ramp up its brightness really quickly. Lovejoy is not a sun grazer and will not be getting that much brighter over the next few weeks. So if you're looking for comets, now's a really good time if you've got a small telescope or binoculars. Hopefully in December you can use the naked eye. Here is a chart. I put this in my slides so that people can look at it and freeze frame the webcast and go, most of you, this means nothing to you. It's passing by Virgo, then going through Serpens, and up here by Hercules. What you really want to know is, where do I look in the sky at what time? Well, the point is in December, you want to look in the morning about 30 minutes before sunrise. This is from our friends at Sky and Telescope. In the east, southeast, it will slowly get higher in the sky. It rises about 10 degrees each week, getting high in the sky. Hopefully, in the first 2 weeks, you'll be able to see some beautiful stuff. Again, the moon is going to get out of the way really quickly. Hits new moon on December 2nd, so it's going to cooperate. Morning is going to be the best time, unfortunately for you evening people. Us morning people are happy. Morning will be the best time to see Comet ISON. You can, however, due to the geometry, also see it at night after sunset. And it will slowly rise in the sky over the course of 2 weeks afterwards. It doesn't get as higher in the sky after sunset. It gets higher in the morning. Pay no attention to these magnitude estimates. They are all hypothesized from previously, and I wouldn't believe them at all. This was made a long time ago. So, if you want to observe Comet ISON, mid to late November, it may be visible before dawn. However, the full moon on November 17th does get in the way. All right, November 28th is when it's closest to the sun, and you should stop eating turkey for just a little bit, go on the internet, find out, did it survive perihelion, go to the Soho website, see if they've got a cool movie like they did for Lovejoy. You know people are going to be processing that really quickly. Early to mid-December, just before dawn and just after sunset. Again, the new moon on December 2nd is your friend, but it will probably fade away before the holidays, looking at the plots estimates of somewhere around December 20th. However, the thing is, we have no idea what's going to happen at perihelion. It could brighten dramatically at perihelion. It could break up at perihelion. Okay? Pay attention to what's going on in order to figure that out. On December 26th, it will actually be closest to Earth, but as I said, it'll be about 40 million miles away, and it will have faded and won't be naked eye visible. It will still be visible in binoculars and small telescopes at that time. Cross fingers. For the observing, you will make sure you want a dark sight. You don't want a lot of street lights in your eyes, even though it's going to be sunrise and et cetera, twilight. And you definitely want a clear horizon. You're trying to get to those 10 degrees, 20 degrees off the horizon. You got a lot of trees and buildings in your way. You're not going to see it, right? Dress warm, bring hot chocolate. It will be December. I don't care if it's the evening in December. Hot chocolate is always good for observing, or whatever hot beverage you so desire. And recognize, of course, that you're always at the mercy of weather and clouds. For updated information, you can go on the internet and do searches, but you can, of course, talk to the local astronomy clubs. There are 3 around the Baltimore area: Hartford, Westminster, and Howard, and they all decided to use the same web address format. howardastro.org, westminsterastro.org, and hartfordastro and howardastro.org. So it's really easy to remember. Go to their websites. If they are doing special events, they're wonderful people. They love sharing their knowledge of the sky. And so I'm asked, where are you going to be for looking at ISON? Where is the best place? Well, I'm actually going to be here. I got a gig with a cruise line where I get to give lectures on astronomy on a cruise ship. And they saw that Comet ISON was going to make a passage, and they said, hey, we'd love to have an astronomer on board. So I'm going to be on the Canary Islands Serenade, which goes from Lisbon to the Canary Islands to Casablanca, through the Straits of Gibraltar, finishes in Barcelona. And I will have a fantastic horizon of the Pacific Ocean to my west for sunset observing. Unfortunately, not everybody can be on there, so do your best to find a good horizon. Resources to help you. Sky and Telescope is always wonderful. Universe Today is good. They've got some great stuff. Sometimes hard to find it on their website, but if you do a search, and you'll come up with a lot of Universe Today things. NASA has the Comet ISON Observing Campaign. You can find them, the CIOC. And the most important thing is going to be the blogs, because the information is going to be changing. You're going to want to keep up with it. We have the ISON blog on Hubble site. There is Waiting for ISON. There's the Sky Live. And the CIOC has their own blog. Finding those blogs is really cool. You'll find out the new information. Now, of course, I can't leave you with all these words. I got to leave you with one last cool comet pic. And this is another picture of Comet Lovejoy from 2011. It's really cool because this pic was taken from the International Space Station. Ain't that cool? Here is Comet Lovejoy. Here is the atmosphere of Earth. And here is Earth and the sun glow on top of it. All right, so that's a really cool comet pic. And I can only hope that Comet ISON comes anywhere near this type of glory. Thank you all for your attention. All right, so do we have any questions about all the various comets and occurrences coming up? Yes?
So, we should thank Neptune for sending objects to become short-period comets, right?
Exactly. All hail Neptune. Neptune is not the giver of the seas, but also the giver of comets, which might actually be the giver of the seas, because the water on Earth might come from bombardment by comets.
So who should be thanked for sending long-term objects?
Ah, there we go. Okay, fantastic. I didn't have time to go through that, but the long period comets are due to Jupiter. So you can't form as far out as the comets out here all the way out at the edges of the Oort cloud. Instead, we believe all of these comets form in the inner solar system from what we call the ice line outward, which is where ices can form in the solar nebula, right? Because up close to the hot sun, you can't form ices. But at some point, it gets cold enough, you can start to form ices. And you'll form all these cometary nuclei type objects from there on out. And then, you'll lose density and you won't be able to form many out here. So many of these go past Jupiter, and Jupiter, with its large, giant mass, shoots them way out into the Oort cloud. All right, and so the idea is that the long period comets formed actually near the inner solar system, but were then thrust out by Jupiter's gravity during the formation of the solar system. And the short period comets never migrated in close enough to Jupiter. They stayed out here, and they stayed around, and they migrated in later. So the ones that migrated quickly got shot out and formed this giant cloud or cloud of comets. Good question. Thank you. I should have, your kind of thing. I would have planted that question had I thought of it. Any other questions? All right. So.